Hi, my name is Andrei Peleas, and I would like to talk to you about automated discovery of privacy utility Pareto fronts. This is a joint work with Brendan Avent, Javier Gonzalez, Tom Dieter, and Borja Bala, and it was mostly done while we were all a part of Amazon Research Cambridge. So the focus of this work is on the privacy utility trade-off from a very practical perspective. Imagine you are in a team that is developing a product or service that uses sensitive data. And at some point, there's likely to be a conversation about how much accuracy or precision of the output of your service the team is willing to sacrifice to achieve certain data privacy guarantee. There are a number of ways one can try and find this balance. Maybe you can go ahead and collect more data. Maybe you can design a better algorithm that gives you a better trade-off. Maybe the privacy analysis isn't tight, and then your best time investment is to get a tighter one. But anyways, in such conversations, you would need very specific numbers so that the team can make informed decisions about how to find this point that satisfies the requirements in terms of both utility and privacy. One example of such dilemma in practice is what the US Census Bureau is facing. After census data is collected and analyzed, it is supposed to be released to the public. Now, in doing so, they're facing two conflicting goals. Data should be made available as much as possible, while at the same time, privacy of the individuals should be preserved. It should also be protected against attacks, such as aggregation of multiple data sources. So the type of privacy guarantee we are using in this work is differential privacy. And here on the slide, you can see a definition of what is known as a epsilon delta differential privacy. Now we use this definition because it works well with machine learning modeling, which is our primary focus. It ensures that an attacker that gets access to the machine learning model trained under differential privacy cannot determine whether the data of a particular individual was used to train the model or not. Okay, so let's consider another example. This time we'll look at it from an algorithm point of view. Here we have a differentially private stochastic gradient descent. Stochastic gradient descent is a basic algorithm used widely in machine learning for optimization, particularly in training neural networks. The idea is to collect a sample of a dataset, compute gradients on the current parameters, make a step along the gradients, and then keep iterating and improving. Now the problem comes when you try to privatize this algorithm. For that, we may clip the gradients, we add Gaussian noise, and so on. And in the end, we end up with 5 hyperparameters that affect privacy or utility of stochastic gradient descent. And we don't have good utility bounds for such non-convex problems, meaning we have no good way of choosing these hyperparameters. Even if we only care about a fixed level of privacy, there are many ways in which we can achieve it. We can increase the level of noise, decrease the clipping norm, and we can do other things as well. So how to pick the hyperparameters so we can get the best utility with such actions, even for a fixed epsilon? Our work is a step towards answering this question. So in order to put such algorithms in production, we would really be interested in having plots like this. This looks very much like the US Census plot we've seen earlier, and this is what's called a Pareto front. Here on the y-axis, I have error instead of utility, and that is for a very small technical reason, which I'll go into later. So basically, what we want to have is a sort of Pareto front that tells us that for a given algorithm or a given model, what is the best accuracy we can get for a set epsilon. And ideally, if you choose a point on this plot, you can even see what is the hyperparameters that gave you this trade-off. Of course, we would like to compute this plot efficiently, which might be a problem in machine learning. because to get just one point here, you may need to train one or more machine learning models. And when you're talking about deep learning models, that can take hours or even days, depending on the size of your data set. But we really want to be able to do this in a reasonable time. So normally, this requirement rules out brute force approaches like a very fine grid on all possible combinations of hyperparameter values. So we also want to be able to use empirical measurements of utility, because in many cases, we most likely don't have the exact bounds on it. And finally, with these plots, we would like to be able to do fine-grained comparisons. So for example, when you have a choice of two architectures of a neural network that you would like to use on a given problem, you'd like to have such plots to understand which architecture gives you a better privacy utility trade-off. Right. So let's try to formulate the problem a little bit more formally. Let's consider a parameterized class of algorithms. A lambda here is an algorithm configuration that we could try, and lambda is a configuration from hyperparameter space. We assume that when we choose setting from the hyperparameters, we can evaluate the error, and it's going to be a number between 0 and 1. For this, we have a utility oracle. We also have a privacy oracle that returns a number between 0 and infinity, and that is the privacy measure for a given lambda, epsilon in case of definition of privacy. I'm going to assume here that I have utility and error oracles in place, but later in the talk we'll go a little bit in discussion of how they could be implemented. So here's what's really going on here. We have some hyperparameter space here on the left. It might be high dimensional, might have a complicated geometry, and we have this two-dimensional plane of error versus privacy loss here on the right. And what we're going to do is we're going to successively pick hyperparameters that might seem interesting to us, evaluate the error and the privacy using the oracles, and will give us a point in that plane. And then we can repeat this over and over again. Then at some point, we get all these points, and we would like to build a Pareto front that tells us that based on the information we have so far, these are the best configurations. Let's call this empirical Pareto frontier. The point here is that this hyperparameter space is huge. So there's a lot of other settings we could try that are not going to give us Pareto optimal points, like that. So I'm trying to determine this empirical Pareto frontier. What we would like is to somehow efficiently explore the hyperparameter space to find the points that are closer to the front and ignore all the rest, not to spend our time and resources. So what we will use here is Bayesian optimization. Bayesian optimization is a well-established technique for optimizing black box functions that are expensive to evaluate. It is widely used for hyperparameter optimizations in machine learning and other fields. It's a big area of active research, and here I'm just going to give a very brief introduction. The typical way Bayesian optimization is formalized when you have an objective is a function f defined in some set of a high-dimensional, maybe not exactly high-dimensional Euclidean space, and you assume that this function is expansive, non-convex, and has some degree of regularity. Now, what you want to do is try to minimize this function by doing as few evaluations of f as possible, obviously because it's expensive to evaluate. Number of evaluations is one metric here. Well, you can imagine that there might be another type of costs attached to evaluation of f. So anyway, we have some kind of budget. And the way Bayesian optimization works is the following. We keep track of evaluations of function f on lambda, and using this data, we build surrogate model for f. Typically, in Bayesian optimization, Gaussian process would be used for that. If you don't know what Gaussian process is, just think that What we're doing here is we use these few evaluations of f to build some interpolation in the hyperparameter space. And this interpolation is probabilistic. It is probabilistic in a sense that it does not only give us an approximate shape of f, but it also gives us some uncertainty around the shape. Now, this uncertainty is key because we will try to find the most promising next evaluation using this uncertainty. So let's look at the simple one-dimensional example. It will hopefully make things much clearer. Here, the goal is to minimize this green dotted line. This is the objective function f that we don't know, and we only have access to it through evaluations. So we want to find its minimum. And here on the top plot, you can also see this blue shaded area, which is the degree of uncertainty of our surrogate model. On the bottom here, we have another plot, and this is so-called acquisition function. The point of this function is to use mean and uncertainty of the surrogate model to point us towards the next evaluation point. The red vertical line right now on the leftmost part of the plot shows us the maximum of the acquisition function, or one of the maximums of the remaining. So at the beginning here we have just one point in the middle. The model doesn't really know anything about f, so we just pick the leftmost point of the domain. Okay, that doesn't look like a minimum, so acquisition function picks another point of the big uncertainty, and this time on the right of the plot. Notice that every time we evaluate the function, we update both the surrogate model and the acquisition function with this new information. So for these few iterations, well, we just evaluate a function in the biggest areas of uncertainty. We're basically just exploring, but then at some point, we're getting really in the direction of the minimum. And at this point, the Bayesian optimization starts to be more exploitative. And we keep probing this region until there is almost no uncertainty left. Okay, so obviously there are more nuances to Bayesian optimization, but I hope this just gives you a basic idea. Now we can explain the algorithm we designed to find the privacy utility trade-off, and we call it Pareto front. Oh, sorry, we call it d-Pareto, and it finds Pareto front. In this case, it's a multi-objective Bayesian optimization because we're trying to minimize two objectives at the same time. We're trying to minimize the error and the privacy loss. And that is that small technical thing I mentioned at the beginning. We use error instead of accuracy because then we are able to minimize both objectives. So in multi-dimensional case, obviously there is no single minimum. There's just the Pareto front of trade-offs, and this is what we would like to find. The algorithm basically implements the Bayesian optimization loop. So we're given a hyperparameter space, we're given the privacy and the utility oracles, and we just start by picking some fixed number of random samples. This way we can bootstrap a surrogate model. Once we've bootstrapped it, we are going to do a couple of iterations, and this time there is a budget of how many times we're willing to evaluate the privacy and utility oracles. And remember, we're in multi-objective case. So here acquisition functions get slightly trickier, and we use hypervolume based probability of improvement. This is an acquisition function that tries to increase the front covers. Okay. So yeah, that's the d-Pareto algorithm. Now, a little bit of a note on the implementation of the oracles. For the privacy oracle, there's a couple of things you can try. You can try get epsilon for a fixed delta. You can also try other variants of differential privacy, or you can use some attack success metrics. On top of that, you may have your privacy measure available in closed form, or you might have to do some numerical calculations for it. We used something called moments accountant in our work, which is an example of this numerical calculations approach. Now, for the error oracle, it can also be defined in various ways. You can think, what is the error for a fixed input? Or you can think, what is the error for the distribution of input? Again, you might be lucky and have the exact expression for the utility or the error, or most likely you will actually have to rely on the empirical evaluations. And yeah, so in our work, here are the choices that we made. And these choices are mostly justified by the fact that we focused our work on machine learning applications. An important thing to note and consider here is that because we use fixed input on the error oracle and we have to repeat each evaluation a couple of times to overcome the randomness introduced by machine learning algorithm, the error oracle might be leaking some privacy. Now, we didn't try to address this explicitly yet in this work, but there are several potential ways to fix it. We could just ignore this issue, or we could use a public dataset, or we could privatize our evaluations and then deal with some increased level of noise at the Pareto front. So on to the experiments. We've run them on MNIST and adult datasets. For the adult dataset, we tried logistic regression with 2 different optimizers, and we recovered these Pareto fronts seen on the top plot. It is obviously a little bit noisy, but it's already allowed us to make some interesting observations, such as the fact that Adam as an optimizer seems better in high privacy regime. So in this plot, high privacy regime corresponds to smaller values for epsilon. For the MNIST, we tried stochastic gradient descent on 2 different neural network architectures. One has a multi-layer perceptron with 1 hidden layer with 1,000 units, and the other has 2 hidden layers, 128 and 64 units. And as you can see on the plot on the bottom here, if you are in high privacy regime, both architectures seem to be doing pretty much the same, but as you move closer to, say, epsilon 0.1, the architecture that has less hidden units is actually doing better than the architecture that might be too big for the problem at hand. So another experiment that we've run is we tried to compare Pareto front recovered with d-Pareto versus Pareto front recovered with random sampling. Now, idea here is that instead of doing any fancy optimization at all, you just pick number of points in random and build the Pareto front around the results. Now, random sampling is known to be a very good technique, and eventually, right, it will recover very good Pareto fronts. But as you can see on the middle plot, on a similar, exact same tight budget, d-Pareto recovers a much better frontier than random sampling. Here in the middle plot, both approaches were given a budget of 256 evaluations. Now on the rightmost plot, we gave random sampling a much bigger budget, 1,500 evaluations, and the budget for d-Pareto remains the same. And you can see the 2 frontiers here look pretty much the same. Okay, so to conclude this talk, first of all, we think that privacy utility trade-off evaluations are very important to enable application-specific decisions, such as choice of neural network architecture or optimizer. And our results show that Bayesian optimization seems to provide a computationally very efficient method to recover this Pareto front. And this is especially useful when your hyperparameter space is huge. So a couple of extensions to this work that we can consider. First is, like I mentioned earlier, we would like to address the leakage in utility oracle or error oracle that I mentioned, like I said before. And second, we could potentially introduce fuzzy criteria in the optimization. For example, running time of the algorithm, right? So now you may have a trade-off between running time, accuracy, and privacy. And there might be other measures as well, and we would like to hear some ideas around that. So that's it for today. Thank you for your time, and thank you for your attention.